In this video, we're going to look at limits that deal with infinity. In this chart, we realize that we're looking at what happens to the variable as it approaches zero from both the left and the right side. As I walk along the x-axis this way and trace along the graph, the values of the y-coordinate seem to go off to very high values. Similarly, when we walk across the x-axis towards the origin from the right side, the graph also takes off towards infinity. So regardless of the directions we approach are either plus or minus 0, again, as these values here get closer and closer to 0 down the page, the values here go closer and closer to infinity, whatever that might mean. But simply to say that these numbers get closer to 0, these values grow without bound. So the way to write this down is the expression seen right here. Just writing that down for you guys to see how it's typically written out. The limit, the limit as x approaches 0 of 1 over x squared equals infinity. Now I'll mention some people will do this a little bit differently and will put an arrow here to infinity, and I'll accept either an infinity sign, either an equal sign or an arrow in this location. On this slide, we'll look at what happens when the x value gets very, very large. It grows from 10 to 100 to 1,000 off to infinity. The function gets smaller and smaller and smaller, getting closer and closer to 0. So as I walk along the x-axis towards the positive infinity direction, the graph comes down the curve and the height variable, the y, gets closer and closer to 0. Similarly, if we were to walk along the negative x-axis towards negative infinity, the graph also approaches 0. These are the two things we see highlighted in the things labeled here and there. In this expression, we look at some different things as what's going on when we have limits going to infinity and limits that are infinity. So the value here, let me highlight with some purple. This value here is looking at what happens to the variable when x approaches a. So as I get closer and closer to a on the left side or the right side, the graph goes off to infinity. So I have this statement written down here. This could be written down as the limit as x goes to a of f of x equals infinity. And again, I could put an arrow here instead of the equal sign. Now the other thing is what happens when the x gets very, very large. As we see, as I go off towards the right hand side of the picture, the output variable gets very, very close to the value of m, being along this dotted line. So the way to write this expression down is that the limit as x approaches infinity of f of x equals m. Similarly, we see this line here. It's what happens when x goes to negative infinity along this curve, this direction. And that can be written down with the expression, the limit as x approaches negative infinity of f of x equals L, and L being the value of the y-coordinate of that line. So this is simply one expression. This is one of the ones we saw on the previous slide. Pop back to a second. This is the one I'm going to highlight here. On the next slide, we simply have the exact same thing. And again, the conclusion we had before is still true. The limit as x approaches a of f of x equals infinity, again, or going off to infinity. This one has the same feel, again, as the x's go to a from the left or the right. Both values go in the same direction, but in this case they go down and get to very arbitrarily large negative numbers. The expression we get right now is the limit as x approaches a of f of x goes to negative infinity, again, or equals. I'll mention the difference between the equals and the arrow here is very small. It's a subtle thing that's not overly important, but you may see it in one or both ways if you use different resources. So this is a slide that you can pause the video and look at the different words here. Simply of different things we can write down. The top one is an example of what we saw 2 slides ago. And this is an example of the top value in that slide, the top expression, I should say. The next one in the middle is what you see in this slide. And we say that this happens and restart. It is very important to highlight that we will make this distinction somewhat, that we are not saying these limits exist. We are simply giving them a statement that has an equal sign. This is why I mentioned the arrows before, where we don't technically have the limit existing as any particular value, but we do make a statement about its behavior. In this behavior, we give some examples. I'll just simply trace out what's going on. As I get closer and closer to the value of 1 from both the left and the right, the graph goes up and up from both sides. So the expression written here is accurate. The limit as x approaches 1 of f of x does equal positive infinity. The other case being what happens at x equals negative 1 from the left and from the right, the graph goes downhill forever. And we get the expression written here, that limit as x approaches negative 1 of f of x equals negative infinity. Now, we've talked about the idea of what happens on the left and the right. Sometimes you will have different behavior on left and right, and it's important to be able to note that. We'll use symbols that we've seen before, I believe, where we have a positive symbol or a negative symbol as an exponent on the value. We have the idea shown here, we'll see those in the next slide, where we have one set of limits from the right side, just above or just more positive than a. These ones are just a little bit less, or the negative side of a. This gives a couple examples. On this slide here on the left, as I approach a from the right-hand side, or the positive exponent, the graph blows up to positive infinity. And the one over here is the same idea. I do approach a from the positive direction, but the graph is going downhill to negative infinity. So even though we have x approaching a from the positive side, the graph can still go to negative infinity. This one highlights the same thing, but from the left side. As x approaches a from the left, because of the negative sign here, the graph goes to infinity, given the expression we see written there. This one has the, again, going from the left side, the graph going downhill, arbitrarily small, given the expressions shown here. So again, notice that we can have negative exponents and positive results, or negative exponents and negative results. Just like in the previous slide, the sign here does not give you any indication what has to happen. You must use the graph. A vertical asymptote is pretty simple. A vertical asymptote is if we have a limit at x equals a, or if we have two one-sided limits at x equals a. So if we have any of these cases, we can talk about the graph having a vertical asymptote at that value. So in this situation, we would have two vertical asymptotes for the graph. There is one along the line that x equals 1, because the limit as x approaches 1 of g of x equals infinity. The line for x equals 3 is a little bit different. There is no limit. If I write this down, the limit as x approaches 3 of g of x does not exist. But it is important to realize that the left-hand limit is negative infinity, tracing from the left side, and the right-hand limit is positive infinity, tracing from the right side. So even though there is no limit at x equals 3, both left and right have limits, and we would call this line x equals 3 a vertical asymptote. This is an expression showing it from a tabular point of view. As we have x getting smaller and smaller and smaller to 0 from the positive side only, this function gets closer and closer to infinity, blowing up to bigger and bigger values. It may be helpful to realize what's going on here, that we have this equaling 5 over x plus 1. As x gets smaller and smaller, 1 remains 1, but we're taking 5 and dividing by a very small number. So you notice the 1 is always sitting on all of these values, that being the one right here. But 5 divided by 1/100th is 500. 5 divided by 1/1000th is 5,000, and so on and so forth. So as x gets very, very small, the values get very, very large. This graph is important to realize if you're going to be using graphing technology. Most graphing techniques using technology will do a connect the graph or connect the dot type graphing situation. So even though the graph should look like the one on the right here, it will often be displayed as the one you see here on the left, where there's a nice vertical line drawn as if it's part of the graph, and if there's a hole in the graph, it won't display it because it simply connects points on the left to the right of the hole. So please be careful when using things of this type, and be careful when using technology that you understand what you really are seeing, and that it may not be as accurate as you may have believed. Last graph here, bringing in some trig, another example of one-side limits. As I take the graph from the left-hand side of x equals 0, the graph goes downhill, giving me the expression limit as theta approaches 0 from the left of cotangent of theta equals negative infinity. As I walk the graph from the right side to 0, I get the expression limit as theta approaches 0 from the right-hand side of cotangent theta equals infinity. Thank you for your time, and I hope this video was helpful.